Hello and welcome. Today, we are jumping into one of the greatest scientific detective stories of all time. It's about a revolutionary and, for a long time, totally ridiculed idea. The idea that the very ground beneath our feet isn't solid and fixed, but is actually in constant, slow-motion flight.
It all kicks off with something you've probably done yourself, just staring at a world map. You look at the curve of South America, and it seems to just slot perfectly into the west coast of Africa. For centuries, people just wrote that off as a weird coincidence. But what if it wasn't?
Okay, so let's break this down. For the longest time, the official scientific story was that the Earth's surface was completely static, fixed. To explain away weird things like finding the same fossils on different continents, they just kind of made stuff up. They imagined these huge land bridges that once connected the continents and then conveniently sank into the ocean. But then this wild new idea comes along. What if the continents themselves drifted apart?
Now, the detective in our story is a guy named Alfred Wegener. And the really fascinating part? He wasn't a geologist. Nope, he was a German meteorologist. And because he was an outsider, he started seeing these connections across different fields of science that all the specialists stuck in their silos had totally missed. And he started building a case. Wegener basically built his entire argument on four main lines of evidence. You can think of them as the four pillars holding up his case file. Now, individually, each one is pretty interesting. But when you put them all together, well, that's when things get really, really convincing. So clue number one went way beyond just the simple jigsaw puzzle fit. Wegener pointed out that ancient mountain ranges, like the Appalachians over here in North America, line up perfectly with mountain ranges in Scotland and Scandinavia if you just close the Atlantic Ocean. It was like he'd torn a newspaper in half. Not only did the edges match, but the lines of text on both sides lined up perfectly. Then you've got the fossils. Scientists were digging up the remains of the exact same small land-based reptiles and specific plants on continents like South America, Africa, India, and even Antarctica. I mean, the old land bridge idea just falls apart here. Were these little guys swimming across the entire Atlantic Ocean? Not a chance. The only explanation that made any sense was that these lands were once connected. And then came the climate puzzles. This stuff is just bizarre. Geologists were finding deep scratches in the bedrock of modern-day tropical India and Africa, scratches that could only have been made by giant glaciers. At the same time, they were finding coal deposits, which form from lush tropical swamps, in the freezing Arctic. I mean, how is that even possible? It only works if the continents themselves had literally drifted through different climate zones over millions of years. So Wegener takes all these clues, the fit of the continents, the matching rocks, the identical fossils, and the crazy climate evidence, and he puts them all together. He comes to this one absolutely breathtaking conclusion. He proposed that all the continents we know today were once joined together in a single, massive supercontinent that he called Pangaea, which is Greek for all lands.
So you'd think case closed, right? I mean, the evidence seems pretty overwhelming. But here's the dramatic twist in the story. The scientific community didn't just disagree with Wegener, they viciously rejected his idea. And not just for a little while, for 50 years. So the big question is, why?
Well, for one, the attacks on him were personal, and they were ugly. He was an outsider, a weatherman meddling in geology. He was dismissed, and his theory was called things like Germanic pseudoscience. There was just this intense institutional resistance to an idea that threatened to overturn everything they thought they knew. But really, the single biggest reason they shot him down, the one case-killing flaw, was this. He had no mechanism. He had a compelling what? Continents move, but he couldn't explain how. The forces he suggested, like the spin of the Earth, were calculated to be millions of times too weak to shove entire continents through the solid rock of the ocean floor. And without a how, his what was dismissed as pure fantasy.
The case went completely cold for decades, long after Wegener had passed away. But then, after World War II, new technologies like sonar, which were developed for hunting submarines, got turned towards science. And for the very first time, humanity started mapping the 70% of our planet that's hidden under the ocean. And what we found? It changed absolutely everything.
You see, the old view was that the ocean floor was this flat, boring, ancient, muddy plain. The reality?
The complete opposite. Sonar revealed a massive 80,000-kilometer-long underwater mountain range that snaked around the entire globe, the mid-ocean ridge. And it found these unbelievably deep trenches. But crucially, almost all of the world's earthquakes and volcanoes were happening right along these strange new features. The Earth's surface was clearly not one solid piece. It was active. This is where a new detective comes onto the scene, an American geophysicist named Harry Hess. He was looking at these brand new maps of the seafloor, and he had this incredible aha moment. He came up with the very mechanism that poor Wegener had been missing all along. Hess called his ideas seafloor spreading. Just picture the seafloor acting like a giant conveyor belt. At the mid-ocean ridges, new crust is constantly being made as magma bubbles up from below. This new rock pushes the older stuff outwards. And then, finally, at the other end of the conveyor belt, the old crust gets destroyed as it sinks back into the Earth at those deep ocean trenches. See? The continents weren't plowing through the ocean floor at all. They were just being carried along for the ride. It was a brilliant idea, but it needed proof. And that proof came from a really strange property of our planet. Turns out, every few 100,000 years or so, the Earth's magnetic field completely flips. North becomes south, south becomes north. And as new volcanic rock cools and hardens at those mid-ocean ridges, tiny magnetic minerals inside it lock into place, like tiny compass needles, creating a permanent record of which way was north at that exact moment in time. And this, right here, is the climax of our story. When scientists dragged magnetometers across the ridges, they found exactly what Hess's theory predicted they'd find, a perfect mirror image pattern of magnetic stripes on both sides of the ridge. This magnetic barcode was the smoking gun. It was the irrefutable, physical proof that the seafloor was, in fact, spreading. The conveyor belt was real. So, with this final, beautiful piece of evidence, Wegener's old idea of continental drift and Hess's new mechanism of seafloor spreading finally merged. They became one grand, unifying theory that we now call plate tectonics. The idea that the Earth's outer shell is broken up into these giant, rigid plates that are all moving around. And today, we don't even have to guess. We can measure this movement with incredible precision using GPS. On average, the plates are moving at about 3 to 5 centimeters a year, which is, funnily enough, about the same speed that your fingernails grow. And this theory just simplifies everything. Pretty much all the geological action, we're talking earthquakes, volcanoes, the building of massive mountain ranges, it all happens at the boundaries where these plates interact. And there are really only 3 things they can do. They can pull apart, which creates new crust, they can collide, which destroys old crust, or they can just slide past each other. And now we even know what's really driving this whole incredible system. For a while, we thought it was just hot currents in the mantle pushing the plates around from below. And while that plays a role, we now know the primary force is actually gravity. It's a process called slab pull. Just picture this. As the old, cold, and really dense edge of an ocean plate sinks into the mantle, its own massive weight literally pulls the rest of the plate along with it. It's like pulling a tablecloth off a table. That gravitational tug is the main engine keeping our planet's surface on the move. Okay, so we've just covered a massive scientific revolution in a pretty short amount of time. So what are the big ideas you should really take away from this whole incredible story? Well, first, a planet isn't some static, dead rock. It's a dynamic, living system that is constantly changing. Second, this story shows that even if you have compelling evidence, a great idea can be rejected for decades if you can't explain how it works. And finally, it shows how a new piece of technology can suddenly unlock a mystery and completely revolutionize our understanding of the world. This one theory explains pretty much everything, from why we have mountains to where earthquakes happen. And this whole process isn't ancient history. It's not over. The plates are moving right now as we speak. So the final thought I want to leave you with is this. If this much has changed to get us to today, what on earth will the map of our world look like in the deep future, say 100 million years from now?